So hi everyone. Today we'll have Grace Sommers. We'll be talking about zero temperature entanglement membranes in quantum circuits, which, as I understand it, is an exciting new use case for SLX calculus, apparently. So I'm very curious to see how that works. Grace, please take it away.
All right, thank you for the invitation to talk here. A little bit of a disclaimer. I think this talk is going to be a little bit different from maybe the main focus of this seminar series. I'm coming from a perspective of sort of statistical physics and quantum many-body physics, but we'll see. Please stop me at any time if there's anything unclear. This is work I did with my advisor David Huse at Princeton and our collaborators Sarang, Gopalakrishnan, and Michael Gullans. And it's available at this archive link. If I can, okay. Yeah, so the motivation for this work comes from sort of a theory that's been developed for understanding how quantum entanglement is produced in local quantum many-body systems, which are able to generate like a volume law entanglement entropy. And so this entanglement production can be described in terms of what are called entanglement membranes, which I'll describe shortly. But these arise naturally when you're considering an ensemble of random unitary circuits, and in some cases they have a rigorous basis in terms of mapping to classical statistical mechanics models. In particular, you obtain the services directed polymer in a random environment, or DPRE. But in this work, we wanted to understand how entanglement membranes can be interpreted in individual realization of some quantum dynamics without any randomness, and so without this ensemble. And we wanted to know to what extent we still apply this picture of the entanglement being the free energy of some membrane. And we also wanted to leverage translation invariance in space and time to get some special features or some exact results on the tangent of this membrane. So in the rest of this talk, I'm going to define for you what I mean by membrane tension. And I'll then describe how we can interpret this in terms of a dynamics that is evolving across a membrane. Then I will talk about how this simplifies in cases where we have multiple unitary directions of time. And then I'll give a couple of examples. I should perhaps warn you that the examples is the part where the ZX calculus comes in, and it's going to be rather basic, but it does give us some nice ways to simplify the circuits and to show that they have multiple unitary directions. All right, so without further ado, here's some introduction to what I mean by an entanglement membrane. So the basic idea is, imagine you're running say a quantum circuit. So here at the bottom, you can imagine you feed in whatever initial state you choose, and then you're running time upward. And then at some later time, t, you want to know what is the entanglement entropy of some subregion, which I've marked with this green line, some subregion A. And the idea of entanglement membrane theory is that this entropy, so the entanglement across this cut between the left and the right, is given by the free energy of some membrane whose top endpoint is pinned to the boundary between A and its complement, and its bottom endpoint can be anywhere on the initial state. And in particular, it chooses whichever path will minimize minimize this free energy. So the free energy consists of this part of the so E of V here is the line tension. So the free energy per unit time here. It depends on the slope V of this curve, which here is on average 0, but it can have little fluctuations. And then there's some contribution from the bottom time slice. So right, so
can I ask some basic questions about this stuff?
Yes.
So entanglement entropy, is this like a measure of how much entanglement there is across these two sectors? Like sort of how entangled they are, these two different parts? Is that sort of the idea?
Yeah, so you could take it to be you could take it to be the von Neumann entropy, or like any Rayleigh entropy. But yeah, it's just it's a measurement, or it's a measure of the entropy of, say, the left side in this total pure state. So yeah, it's how much it's entangled with the right side.
Okay, and then I could understand like what the interpretation is if you do this across a space dimension. Like if I make a cut in the space dimension, I can say, well, okay, like these qubits, how entangled are they with those qubits? But now you're also going through time. Like what is kind of the interpretation of that in terms of entanglement?
Okay, yeah. So so there's sort of two different things happening here. So the entropy that we're measuring is the entropy of this particular region, which lives on this boundary of like the spacetime, this green interval here at the top. And so that just lives at some time slice. But the entropy on that time slice has been generated from this time evolution, starting from some initial state. And so in order to quantify that entropy, in terms of this membrane, the membrane is this black squiggly line. What I'm saying is that the entropy at this later time t is given by the free energy of this membrane that goes from that time t all the way back to time 0, separating the left side, which I've shaded in light green, from the right side, which is shaded in light red. But the entanglement is defined on a state that's just defined at time t.
All right, thanks.
All right. So in this equation, we have this minimization over any possible bottom endpoint. So we can't directly know what the slope v that the membrane will actually take would be. So the way to actually determine what this line tension E of V is, well, one way to do it is the following protocol. So you imagine that, say, at some early time, you started from just a product state, then the membrane could attach anywhere, and there would be 0 cost at the bottom, because it's unentangled. Then you run for some long time with a cut down the middle. So you're generating 2 scrambled halves. So the left half of the system and the right half of the system, where the center is denoted by x equals 0, become nearly maximally entangled within themselves, but there's no entanglement across the cut, which means that this endpoint here, so then at time t equals 0, now you allow them to interact. And the idea is that if you're within the so-called butterfly cone of this endpoint here, where you terminated this cut between the left and the right halves, you can attach to that with 0 cost. So like the sy of 0 will be 0 if you attach there. And then therefore you can watch as the entanglement between the left and the right hand side fills in. So for example, here at the top boundary, I'm indicating the entanglement of this marked blue region, these blue qubits. And I'm saying that it will be the cheapest thing for the entanglement membrane to do would be to attach to this point here, and then so this fixes the endpoints. And I know VT is just the distance from the center. So what this looks like in terms of a random circuit is that as time advances, the entanglement as a function of x, which is the distance from the center, it starts, so let me just restart this video. It starts as 2 page curves, so 0 at the center because they're not entangled. And then as time increases, the entanglement inside here fills in, and the orange region is the part where we know that the membrane is attaching to the center. And so from that, we can just extract what the line tension is just by dividing this SXT divided by T. So this is one way to pin both ends of the membrane and figure out what this line tension is. However, there's a slightly different interpretation, which is now we're going to turn things on its side, and we're going to imagine instead of looking at the entanglement between, say, some subsystem A and its complement, we're going to consider a dynamics where we start from a fully mixed state. So this is just the density matrix is proportional to the identity. You can imagine taking each of these qubits and entangling them with a reference qubit, but you can also just think in terms of the density matrix. And now we're imagining that the dynamics that is running in this particular direction doesn't have to be unitary. It can involve measurements or other projectors. They can be forced measurements, for example. And then we run for some time, and we see what is the entropy density of the state at a later time. And this entropy of this state now will be given by a membrane that's running horizontally, separating the final state from the initial state. And so if this entropy density converges to some non-zero finite value in the particular limit where we take a really large system first and then take the time to go to infinity, so essentially forcing this membrane to go horizontally because it's much wider than it is tall. In that case, we're going to call this output state with entropy density S a plateau state, because it basically, in certain examples that we'll see, it just starts fully mixed, goes to some entropy density, and just sticks there. And in that case, this entropy density S would just be, because it's a density, it would just be this line tension of a membrane that is running horizontally in this picture, which is parallel to the initial state. So from this interpretation, the way that we've pinned the ends of the membrane is just by taking this particular limit. And if we imagine having some circuit, we can, and interpreting it as, say, a tensor network, we can run time in any direction, just like evaluate it in a certain direction. And finding this entropy density would tell us the tension of a membrane parallel to the initial state that we chose. And so from this interpretation, understanding how this line tension depends on the angle at which we put this membrane comes down to understanding what are the different types of dynamics that we can have running across this membrane. So in this picture, going upward in time, where we now are choosing time to run in whatever direction we choose. And so it turns out, well, we sort of break it down into 4 increasingly less restrictive classes of dynamics, and in this talk I'll mostly focus on the first 2. So the simplest type of dynamics is when the dynamics going across this membrane is fully unitary, and that highly constrains what the line tension will be, as I'll explain in a moment. Slightly less restrictive than that is when it's not everything the full Hilbert space, but it's unitary within some subspace of the full Hilbert space, and or even slightly more general than that, when it arrives at some permanently stable plateau. So you start at fully mixed state, you run to some for some short time, and you get to some entropy density S, and then you just stay there. The third case, which I'll touch on briefly, is when you don't have a permanently stable plateau, but it is almost stable. It's like an emergent plateau where the purification events, which decrease entropy density, are very rare. And then the fourth case of generic dynamics, I won't really dwell on too much. The reason why we're interested in these first three classes is because they include all Clifford circuits, so all stabilizer circuits, which we can classically simulate, including with stabilizer measurements, running in any arbitrary direction. And when there's this emergent or permanently stable plateau, the free energy of the membrane behaves like the free energy of some short-ranged classical lattice model at zero temperature. So in other words, the free energy is really just the same as the minimum of the minimum energy. So there's no temperature involved. And if we further restrict to Clifford circuits, which are translation invariant in space and time, so we can imagine, say, every gate being the same, then in that case, we get this either permanently stable plateau or full unitarity. And in that case, the zero temperature behavior manifests as the line tension just being piecewise linear as a function of the slope. So you don't have any of these fluctuations because we've gotten rid of the randomness. So I said that the case one where it's fully unitary highly constrains what the line tension can be. And that's because if we imagine, so in time, so we imagine setting down some member at some angle, say this arc black line here. If that membrane surface is space-like with respect to some unitary arrow of time, so we imagine, say, in this picture, so each of these little purple gates here is a unitary gate. Then if we go forward in time, if we take time to go upward, there's this light cone, which I've shaded here in gray, and that's all the time-like directions, or time-like or light-like. And so if we're outside of that, such as in this example here, then what that means is that we're not going to, if we run a dynamic that's perpendicular to this tension here, then we're not going to, the entropy is just going to be constant, because we can just contract a bunch of unitary gates. And so the free energy will just be the number of qubits, the density of the qubits across the membrane, which if we write this line tension in terms of like a free energy per unit time, then that means that E of V is just absolute value of V. And so, in other words, whenever this V is outside this light cone velocity, which in this case is just 1, we just have this linear form. Okay, but what about inside the light cone? So in the picture I showed, or in the movie I showed, where you pinned the two ends of the membrane and watched the page curve fill in the center, that was looking at V that was inside the light cone, which is like where the interesting stuff happens. Well, there's a special case that we'll consider first, which is when there's another unitary time direction running in the spatial direction. So such circuits are called dual unitary, which just means that not only are they unitary going forward in time, but they're also unitary if you contract them sideways like this. And so that gives us this other unitary time direction T prime, which has its own light cone, this shaded green light cone. And so now if we have a different, if we take a different membrane orientation, say the one shown here in black, then that will still be space-like with respect to some light cone. So it cuts into the original shaded gray light cone. So it's not space-like with respect to that, but it is space-like with respect to this green one. And so we can again use the unitarity condition to exactly evaluate what the line tension will be. And in terms of, because of the way we took this to be per unit time, it ends up that E of V is just going to be 1 for any V less than or equal to the light cone velocity. And there's a different way to interpret this in terms of, or sort of a way to put these different time directions more on equal footing, which is instead of taking the tension per unit time, where time is going up, we can consider the line tension per unit length of the membrane. And in that case, for the dual unitary circuits, that just means that this new tension, which are called E tilde, as a function of this angle with respect to the horizontal, it's just the maximum of cosine theta and sine theta. So it's just, so here you can't really see the piecewise linearity, but what you see is sort of a smooth function that then has these cusps at the edge of the light cone. All right. So now before I dive into some examples.
Sorry, can I ask a question? So just now you said that these two shaded area are the light cones that are the interesting part. Could you explain a bit more why they are of interest and what do they stand for?
Oh, I guess what I mean is like, say you have a unitary circuit. So say we go back to this picture, and I'm saying all these little gates here in this brickwork circuit are unitary. Then unitarity imposes that it imposes like a finite light cone outside of which you can't have you can't have any correlations or anything. It won't know about what's happening if you're, stuff can only propagate so fast, right? So in the context of this, what it means is that if you're outside the light cone, the entanglement entropy can't have changed from what it was at time is 0, because we only change things at the center here. So the far away qubits outside the light cone don't know about that change yet, so they're just constant. And or sorry, the entropy there hasn't changed from its time 0 value. And so the reason why I said the interesting stuff happens inside the light cone is because sort of outside the light cone, it's sort of just trivially imposed by sort of a density of qubits going through the membrane. There's really nothing else it can be. That's basically what I meant. Like in the sense of any unitary circuit will have this behavior, but it's very special to have this behavior inside the light cone that requires having a second unitary direction. And these, I should mention, these dual unitary circuits have been studied in a lot of different papers, and they're used as a model for quantum chaos, and you can solve a lot of things exactly, like operator spreading and entanglement growth, spectral form factor, etc. So as I said, this is sort of a special case when we have unitarity in both directions. But if we loosen that a bit, let's say
I'm sorry, can I could you give an example of a unitary that's dual unitary? Because all the examples in my head don't work. Like the identity is not dual unitary. The C-naught can
yes, so the identity is it fails badly to be dual unitary because it's a projector in the other direction. An example that's dual unitary is the swap gate. It's just if you tilt it on its side, it's still a swap. So in fact, the if you're restricting to Clifford circuits, which I often do, the only the types of gates that are dual unitary are up to single qubit. You can dress them with any single qubit gates you like, that doesn't matter. But the 2-qubit core can either be swap, which isn't that interesting because it doesn't generate entanglement, or iswap, which generates entanglement in sort of a maximal way. But for example, C0 would not be dual unitary, and identity, as you said, would not be dual unitary. So going beyond dual unitary though, we can, the second case that I want to describe is when there's a, when we run the dynamics across some membrane, so we're choosing some arrow of time, which isn't, now we're saying it's not unitary, but we reach some plateau subspace that has an extensive entropy, and this entropy, the full spectrum of this subspace, so like this steady state density matrix, is not changing in time. Then oftentimes the dynamics within the subspace is actually unitary, and also has it preserves the locality, so it has its own sort of effective light cone. And in that case, basically the same stuff that we found for the unitary case still applies, just it's no longer the number of qubits flowing across the membrane, but it's the number of it's sort of the dimension of whatever this subspace is will fix what the tension is. And basically, as long as you stay sort of outside one of these effective light cones, or you sort of what we'll call a light sector, then basically you just get something linear. The membrane tension is just linear in the slope, and so you end up with this piecewise linear behavior where the discontinuities in the slope are just at the boundaries between these light sectors. And I will give some examples shortly. And we'll say that a model is fully multi-unitary if any membrane can be described in this way, meaning that the union of all these light sectors, where we have this linearity in the slope, covers all possible orientations. So we already saw an example of that for dual unitary, because either you can consider it unitary with respect to space or with respect to time, and that covers, there's just 4 different sectors, and that covers everything. The examples that I'll be giving today will mostly fall into being tri-unitary, which just has 3 arrows of time, and some more recent work about both in higher dimensions and also still in 1+1D of generalized dual unitary, where it's not fully unitary, but it has this unitarity within a subspace. And I should mention, if you take a circuit that is composed of all identities or all C0 gates, which, as we said, was not dual unitary, it is this generalized dual unitary, because the spatial direction has this permanent subspace. In the case of identity, it's just first state. It's sort of dumb, but the case of C0 is quite interesting. All right. So one more slide before I show some spiders. So to sort of visualize what I mean by these light sectors, this here I'm showing is a case of where we have 6 different light sectors. So this occurs when we have tri-unitarity. So we have the usual time to say we have the usual direction going upward, which is unitary, and then we have the directions at angles π/3 and -π/3 with respect to that. And basically, to each light sector, we can associate some time vector t, which in this case is just in the center of the sector, such that we can imagine basically if you take this membrane. So what I'm showing here for the membrane is that the black arrow, so I have the membrane going in the orientation, the black orientation, and the arrow is its normal vector. So whenever the normal vector will point within one of these 6 sectors, yellow, red, blue, and the per unit length line tension will just be given by the inner product with whichever is the closest, or with the t hat vector that's at the center of that sector. So whichever of these 6 arrows is closest, you'll take the inner product with that, and that will give you this per unit length line tension. And so again, you can see like right here, it switches between yellow and blue, and then here it switches between blue and red. That's when you'll have these sort of discontinuities in the slope of this line tension. So I want to give some examples in one dimensions. So the first example will be one of these generalized dual unitary circuits, or it's called DU2 because it's the second level of the hierarchy. And you can get those by having a circuit with where each of these gates, so I'm imagining now I'm taking a Clifford circuit, and I said it was spacetime translation invariant, or STTI. And in particular, in this case, I'm going to take the unit cell to have 2 gates, U1 and U2, where U2 is just the left-right reflection of U1. So U1 is just a C0 dressed with some single cubic gates, and then U2 is just a C0 going in the other direction. So if I sort of take a little bit of liberties with the ZX diagram notation and just right now denote U plus and U minus just as being in these boxes, then the C0 gates, we know what they look like. This green and red spider joined like this. Then what you get is that this brickwork circuit, which you would think would have a sort of a square lattice type structure, when you write it as this ZX diagram, it ends up being defined on this honeycomb lattice. And the honeycomb lattice naturally has these 3 arrows, what has a 6-fold symmetry up if we were to ignore these single cubic gates. And we know that if we run time in the forward direction, or sorry, the upward direction, that's what the upward direction is, where we get this decomposition into these C0s and not Cs, and that's manifestly unitary. So from that, we know what the, right, that gives us this, this first sector, this red sector. But what about the 2 other directions? So basically the question we want to answer is, if we rotate by pi/3, is that dynamic still unitary? And so it turns out, so I kind of take another abusive notation where, because this U might not be equal to its transpose, I sort of tilt it a little bit to just show that the time is going upward. Then this gate, which has, so this is the gate that you see if you tilt your head to the right and are going through this way. This gate has this form, and so it's going to be, because it's just a matrix, and it'll be a unitary matrix if this condition is met. So for example, if U is a Hadamard, then this condition is met, and because that will just give you a CZ gate. And so if we look at the dynamics going along either the pi/3 direction or the minus pi/3 direction, the gates that we encounter are these 2 ones. And so each of those imposes this condition in order to be unitary. And so if we choose U minus and U plus to satisfy these conditions, then this circuit will be tri-unitary. And then we can just apply what we found here. So in particular, an example where that occurs is if you take U minus to be, so again, these are all Clifford gates. If you take U minus to be this rotation about 1, 1, 1, and if you take U plus to be just a pi over 2 rotation about the x-axis, then you get a triunitary circuit that is good scrambling, meaning that it's chaotic and it generates entanglement starting from a product state. And here what I'm showing is that protocol that I showed at the beginning in the movie, where I start with two subsystems that are separately scrambled, so they form these 2-page curves. And then as I run time forward, so the increasingly dark colors, I see that the entanglement increases filling in here, and from that I can deduce the line tension, and it just takes this form. So this V for this part comes from the unitarity of the one-time direction, and then the inside part comes from the unitarity along the 2 other directions. How much time do I have?
We started 10 minutes late. Let's say at least 15 more minutes, but if you want to go longer, then it's also fine.
Okay, all right. So yeah, so the second example I want to show in 1+1D, because I just want to make sure I also have time to show some 2+1D examples, is sort of something where ZX calculus helped us realize sort of what was going on here. So we start with an even simpler example, where now we just have the same gate at every so we have this brickwork circuit where every gate is identical, and we take it to be this is an example of a dual unitary gate. So you have the I swap gate, and then we just dress it with an X rotation on one leg, and then some other Clifford gate U on the right leg. If we cross it, then the page curves will fill in like so, and that's just the dual unitary line tension that I was saying. So inside the light cone, it's just E of V is 1, and outside it's just V. So things just fill in this very sort of boring way, but this flat line tension is characteristic of the dual unitary circuit. Now, let's say we add measurements. We're going to put measurements in the X basis on the leg entering the left in every other layer. If we do this, then we can so now we have a non-unitary circuit running upward in time because we have these projective measurements. But if we do the same protocol, what we find is that we sort of get this sort of asymmetric, but still piecewise linear type of entanglement growth. So it's flat on this sloping like V on the other side. And it's sort of like it only has a few discontinuities in the slope, right, at here and here, for example. And so it seems like there should be some interpretation of this in terms of light sectors, right? Like and so that's what we wanted to figure out. And so it turns out that this example you can also write, of course, as a ZX diagram. And if you write the I swap in sort of this funny way as being like a C, I guess you take Z rotations, follow it with a CZ gate, and then follow it with a swap. Then when you put in the measurements, so on alternating layers, you'll have where you do a projective measurement after the I swap gate. So that's and because the measurement outcome doesn't affect the entanglement, like whether it's a plus or minus 1, we can just imagine post-selecting on always being, say, in the plus state. And so then we just get, with just some simple fusion rules and like twisting things around, we get this. And similarly, entering the next gate, we have, because we just measured the 1 qubit, and so we've put it into the plus state, then we can just similarly simplify that to look like this. So now we've gone from these sort of 4-legged tensors to just these 3 junctions. And it turns out if you sort of move things around and make them look nice, you just get another honeycomb lattice. But this time, if you look at it carefully, you'll notice that the standard time direction, the time direction that we chose when we wrote it out as a brickwork circuit like here, that standard time direction is actually, it's rotated an angle of pi/2 from what it was in my first example. So it's not aligned with any of these unitary directions. But we can ask the same question of whether, if we define time going in any of these arrow directions, whether that gate will be unitary. And if it is, then we have this associated light sector. And in particular, if we imagine running time flowing upward, particular boundary condition, then even though the circuit as originally defined has these measurements, we can actually, if we cut the legs like halfway inside one of these measurements, so we have like half the dimension of the Hilbert space, then we can actually make this be a fully unitary circuit, provided that both this direction going through this way and this direction going through the pi/3 rotated way, if those are both unitary, so these green and these yellow gates, then this is a fully unitary circuit. And that explains sort of why it has this, if I run this circuit, it has a plateau entropy of 1/2, and it's just coming from the reduced Hilbert space. So indeed, if we choose, say, U, so we had this freedom of this one gate U, if we choose it to be this particular gate, then with a certain way of cutting up the legs, we actually find that the gate, like each of these gates, this thing can just be written into having everything be a C0 gate. But as I said, things are rotated by pi/2. So this is a circuit where every gate is C0, but we're running it sideways. The circuit where every gate is C0, the brickwork circuit where every gate is C0, is called the Clifford-East model. And running it sideways, like I said, is not unitary within the full Hilbert space because C0 is not dual unitary, but it's unitary within half of the Hilbert space. And so once we've deformed onto the honeycomb lattice, then we can run this circuit again. So this is just like a change of just some deformation of how we defined X and T. And then we get this symmetric form for the one tension, which is just the pi/2 rotated version of what we saw in example 1. Right, so those were two examples. Yes.
You said like it's unitary in half the Hilbert space, but this I think you explained it, but I didn't quite catch that, like what that means exactly.
Yeah, so in the original circuit, we have like so how do I want to say this? Basically, you can imagine it as follows. This little red dashed line, you can imagine defining a state on this, and then on that, along that line, and then it's defined on, say 1, 2, 3, 4, 5, 6 qubits. But you could also have cut time right in the middle here, and then it would be on twice as many qubits. And basically, when we run the original circuit here, we're defining it on twice as many circuits, because twice as many qubits, because just we're counting every qubit that's entering the gate. But half of those qubits immediately get purified because of so like if we feed in a fully mixed state, half of them immediately get purified by these measurements. Or viewed in another way, the C0 gate, if you rotate it sideways, so like if you imagine it being sort of like this thing here, like this guy going through it in this direction, it will involve, right? So the first guy is like doing, it reduces the entropy by 1 bit. And then yeah, so basically it's a matter of cutting it here, and then you have 2 qubits versus cutting it here, and then you have 1 qubit. And so you only have 1 qubit of entropy that actually survives, and that's why if you do this protocol of running the starting from fully mixed, then you'll immediately go to S is 1/2, and that's what sets the line tension. Yeah, so all right, so with my time remaining, I want to show an example in 2 + 1D. So here's the example. This is called the square lattice parity model. And basically what it means is you imagine you have a square lattice of qubits, and on alternating layers, you're either going to take a C0 gate between, so you have a square lattice, so you have an A and B sublattice because it's bipartite. On odd layers, you're going to take every qubit in the A sublattice and do a C0 gate with that qubit as a control to each of its neighbors. And then on even layers, you're just going to switch which one's target and which one's control. When you do this, then sort of the operators spread, or like the stabilizer generators spread in this pattern, sort of within these squares that are rotated by pi/2. But if you write this as a ZX diagram, it's just a simple cubic lattice. So you imagine time going upward. Yes, you have to be a little bit careful about, yeah, so if you cut the qubits here, you're feeding its initial state, and then you can sort of merge these C0 gates in such a way that you just get this cubic lattice where it's alternating green and red spiders. And so from this, you can immediately see that, well, we know we have this unitary representation if you go in the z direction in time. And since this cubic lattice is, fully symmetric under rotations like switching x, y, and z, we know that we actually have unitary directions in the x, y, and z directions. So it's maybe hard to see from this that it's unitary if you go forward in time, because each of these is a projector. But we have this explicit, right? We know that it's a unitary circuit, and so therefore it's going to be unitary in each of these 3 directions. And so that actually gives us these 3 light sectors, which I've shown here. So they're these pyramids, the ones that are outlined. So the operators, the light cones are these smaller pyramids outlined in white, and the light sectors are these big pyramids that fill in this cube. And then the line tension, well, now it's not a line, it's a surface tension, is just given by the maximum of, so you take some membrane, it has some normal vector, and you find of these 3 directions which one is closest to that normal vector, and that gives you the membrane tension. So in terms of the entanglement growth, we can imagine starting from some state where we've separately scrambled the 2 subsystems of this. So now they're in 2D on either side of some membrane. So some cut. And then we run in time and we look at the entropy at some later time, such that basically we've pinned we pinned the ends of the membrane to now points, we pin them to these lines. So for example, I'm showing this black membrane here, and its normal vector points inside this red light sector. And it turns out, if you convert this back into what it would look like in terms of the entanglement growth as a function of time, it actually just grows like linearly like this, with flat in the inside. And so this verifies sort of this ansatz for the line tension. I had a second example, but I think I'll skip it because it's just sort of another example of how you can construct a different model where now it's a BCC lattice of spiders, and in that case you get the light sectors form this octahedron. I just want to briefly mention that sort of in this talk, I focused on these specialities. So the Cliffordness of these circuits that I mentioned was not actually critical. What was important was that they had these multi-unitary, so they had multiple unitary directions. So you can make, for example, a dual unitary circuit, which is non-Clifford, and it will show the same behavior. The reason why I called it T equals 0 is because if you imagine this membrane, when you take its free energy, as you run time, it has more and more places where it could go. And in the partition function, those would all contribute to the free energy. But the fact that the entropy is staying constant means that as you add terms to the partition function, the energy is not changing, which means it only cares about the lowest energy test. So that's the sense in which this is a T equals 0. And so if you generalize beyond this to, say, random Clifford circuits, then now you'll have these, it will no longer be a strictly constant plateau entropy, but it will be sort of exponentially rare purification events. And so each purification event is just associated with finding a new minimum energy. So this situation is also described by, it's also effectively 0 temperature, but now it has these random, so it doesn't have any thermal fluctuations, but it will have fluctuations due to the disorder of the random gates. So this example is where it's important that it's Clifford, because in Clifford circuits, the entropies can only be integers, so it really forces these purification events to be exponentially rare as opposed to just slowly purifying. And then class 4 is sort of just everything else, where I guess the only useful thing we have to say is that we don't expect it to be 0 temperature because it doesn't have this stable plateau. So with that, I would like to summarize by just saying that sort of the way that we interpreted these entanglement membranes in an individual realization of a system as opposed to an ensemble was in terms of the sort of the flow of entropy, or you could say of information across a membrane. And by considering the different types of dynamics across that membrane, in particular those cases where it's either unitary within the full Hilbert space or within a subspace, in that case we can divide the set of the possible membrane orientations into these light sectors, and get this full description of what the tension of the membrane is. And the place where ZX calculus came in is that it helps simplify these circuits and elucidate which are the unitary arrows of time. And this interpretation of the membrane in terms of this information flux extends naturally to higher dimensions, where we looked at these examples of just very simple examples of phaseless X and Z spiders, and saw how we could construct the light sectors in those cases. So I'd just like to thank my advisor and my collaborators, and thank you for your attention.
All right, thanks, Grace. Everyone can thank our speaker with using the clap emoji on Zoom. And do we have, or like real clapping is also fine, of course. Do we have any questions? Yes, Leo.
Thank you so much for the really interesting talk. My question is about the simulation. Like how would you, what exactly is implemented in the simulation? Like when you switch time arrows, is it like a Monte Carlo step, or what is, how do you compile the circuit differently in real time, or how does that work?
Yeah, so for a lot of this, I don't actually have to run the circuit because like we can just find it theoretically, but all we're doing, so for example, maybe the best place to explain it is just in this original example of how we find the line tension here. In this case, we're just choosing one direction of time, so we're just running this unitary circuit. We're just doing a stabilizer tableau simulation, so it's efficient in time, polynomially efficient, and we don't actually have to. We can get all of these angles within the light cone in just one run, because we pin the one endpoint, and to pin the second endpoint is just looking, so at each time slice, we just compute what is the entropy for each x. So, and choosing what x is, or which is VT, choosing that just pins that endpoint. So all we're doing is just running a unitary Clifford circuit in one particular direction. For the thinking about different arrows of time is more of a sort of a useful construct, but we're not actually like compiling a different circuit each time or anything.
Thanks, that helped. And how close is the approximation of that these are Cliffords? Like what kind of models, and what exactly is the error term or expansion if you're using Clifford circuits versus the true dynamics?
Oh, so the dynamics is just the Clifford. I mean, like that's the dynamics we're choosing. We're not approximating it. We're just considering some dynamic, we're considering a unitary, we're not considering rising any Hamiltonian or anything. This is just consider some model in which your time evolution is given by this Clifford circuit.
Thank you. It was really interesting.
Thanks.
Okay, any other questions? Yeah, Sarah?
Thank you, Grace. I wonder, when you talk about this geometric interpretation will extend naturally to the high dimension, wouldn't you get to wouldn't the diagram get clustered really quickly, and or this will not be a problem, like when you go to the high dimension?
I guess what I was just referring to is, like, for example, here we're in 2+1D now, or in terms of the diagram, it's just defined in 3D. And now we don't have a line tension, we have a surface membrane, but we can still define, so in this case, my model is just defined by this unitary time evolution, or if you will, it's just defined by this ZX diagram. You can choose time to run in any direction, but like there's no real obstacle that I see. I mean, you'll have to be, if you want it to be a fully multi-unitary model, you generally have more constraints on the gates. So there's been, like, in the dual unitary literature, there's been stuff done on what are called ternary unitary gates, which are these these plaquette operators. So like in a 2+1D geometry, you can consider like plaquette operator gates that are unitary in 3 directions. So it's sort of like that. So I guess it makes it more constrained if you want it to be fully multi-unitary, but it's not an obstacle in terms of like the analysis, really.
And just now you gave 4 cases, and you said the top 3 are entirely represented by the Clifford circuit, and the last one, is that the last one that lives outside the Clifford group?
So I should clarify. Classes 1 to 3, we claim that like any Clifford circuit, not necessarily unitary, so it can have measurements or forced measurements, will be in one of those classes, but there's stuff in that class that's not Clifford. Because I mean, like, you can have for instance, first of all, the class doesn't describe, like, a given class just describes like for a particular membrane orientation. So for instance, any generic unitary circuit, say a Haar random circuit, the membranes that are outside the light cone will fall into class 1. The membranes that are inside the light cone, or inside the butterfly cone at least, will fall, generally speaking, into class 4, because they don't have this stable or emergent plateau. So yeah, so that's why Cliffords are nice, is because, so what we're claiming is that basically, even in a random Clifford circuit, the entanglement membranes will be like microscopically at 0 temperature, whereas in a random non-Clifford circuit, you'll have thermal fluctuations in this effective StatMech model. I don't know if that really answered your question, but
yeah, that helps a lot. Thank you.
Yeah, so you mentioned that this example where the dimension of the Hilbert space was halved, or actually square root, and that was a feature in one bi-unitary circuit which was translation invariant. Can you say something in general for other circuits which are translation invariant? What the sort of the surviving dimension will be? I don't know if this is what you call the plateau entropy.
Yeah, so okay, so a few things. So one is, if you have a Clifford, and say you can consider a Clifford circuit with, you put in some measurements and you make a translation invariant, then in general, it will, if you start with a fully mixed state, it will purify a little, like the first round measurements, where you have an extensive number of measurements because you have like some number of unit cells that are all the same, will lead to some amount of purification, and then subsequent measurement rounds can lead to further purifications, or you can just stop. At some point, you can just stop purifying, and you reach, because the flow K circuit, that's translation invariant in time, once you reach like a steady state, we show that like once you reach this plateau state, then it's just like repeats for all time. Now, of course, that plateau state, in which case, so you could just purify completely, in which case this entanglement membrane picture isn't, you don't have a volume law amount of entanglement, you're just pure. So it's kind of, you could imagine it be, you could say that, you know, the entanglement velocity is just 0 in that case. If it's not Clifford, this hierarchy of, so these, maybe show the reference. So there's been a lot of recent work that sort of inspired us about generalized dual unitary circuits. And those are circuits basically where there's sort of in a hierarchy of conditions on the gates, which basically impose at least the first level of the hierarchy, du2. It's that it basically imposes precisely that the spatial dynamics are, so the time direction is fully unitary and the spatial direction is unitary within some subspace, and the dimension of that subspace is related to the well, it's related to the Schmidt decomposition of the operator, but it relates to this entanglement line tension in a fairly simple way. And so yeah, the first reference of that would be, I think, Yu et al. And these references here are all about generalized dual unitary.
Thanks.
So Grace, I had a question about like when things can be dual unitary and stuff like that, because the examples you gave, they were all maximally entangling, and like if you're working with Clifford circuits, that's of course a requirement. I was wondering, are there like dual unitary or tri-unitary operations like outside the Clifford fragment which are not maximally entangling in certain directions? Perhaps where they are like
so well, okay, so yeah, dual unitary, it's sort of proven that so if you start from a certain so there's what called these solvable initial states. An example would be just like you start with a state of bell pairs. Then like by analyzing these various tensor network diagrams, you can show that like the entanglement, say across like half of the subsystem, like half of the circuit, it increases like at a maximal rate. So for example, like in a swap circuit, that's sort of simple to understand because you're just taking these bell pairs and like, you know, you have like a quasi-particle description of the entanglement, just like as you separate the bell pairs going across the middle of the cut. So that's not really genuinely generating entanglement, but it's sort of moving it around. Whereas in the say like the I-swap circuits or other in any other dual unitary circuit, you can start from like a product state and actually generate entanglement. But right, so basically, yes, so there's sort of I would say two different facets of the dual unitaries. One is that, yes, for certain solvable initial states, the entanglement line tension, basically the fact that the line tension is flat inside, that shows that it's maximal. So that's one factor. And the other factor is within the class of dual unitary circuits are some that are like ergodic and others that have these like conserved charges and are non-ergodic. And so there's sort of a hierarchy of chaos within the class of dual unitaries.
Maybe I can pitch in to give an example that was for this dual unitary. So you mentioned the I swap. So that's essentially just the swap where you add a phase whenever the two inputs are 1. And now this phase doesn't need to be I, it can be any unit phase. And this will still be a unitary and has an interpretation, a physical interpretation as, okay, you have two particles that can or not be there. And if they're both there and they cross, then they accumulate a phase. And this phase can be anything you want. So this is outside of the Clifford, unless the phase is I, but it still can be simulated with a solvable model, which is the matched gate tensors.
So for example, the bare I swap circuit, so a circuit just has only I swaps, is an example of this match gate circuit. And so it's actually a case that is not, if you just have I swaps, it's not like ergodic. It has these what are called gliders, because if you like feed in a Z operator, it'll just propagate like along a diagonal. But yes, but then there's a separate class that's not necessarily, or an intersecting class that's not necessarily Clifford, but is also classically simulatable because of this mapping to like free fermions, basically, as Fernando was saying.
So also the question about this example you gave where you have some internal measurements, but then like you can actually see that they fuse into the spiders and you get a hexagonal grid. And then the time direction, you sort of need to go from like going straight up. You need to sort of tilt it a little bit to get something unitary. I don't really have any specific question. I just think this is really interesting. And I was wondering, like, does this have any use cases outside of this? Is this useful for like quantum computing people to realize that like sometimes when you do a measurement, this actually tilts your time direction?
Yeah, I don't know exactly what the use case would be for like quantum computation. Yeah, I'm not sure, but it is sort of neat that like it's an example where I guess from a different perspective, you could say the initial underlying symmetry of the circuit is that of a brickwork circuit, which is like but like that's the systemic how and so by the initial choice of representation, but you can bring it out if you use a different representation.
Yeah, it reminded me a bit of what happens in flux classification of error correcting codes. I think Alex Kojil here in the chat, I'm not sure if he's still around. I think he's doing stuff with that, but like also like you have your error correcting code, but you're splitting up your stables in such a way that actually you sort of have this like timeline direction that is sort of like wiggling around in your space. And that's kind of what it reminded me of. Again, I didn't have any specific question. I just thought it was really interesting. Are there any
another
other
comment? Another comment is that we looked at the structure of fault-tolerant protocols like the surface code. And when you do this simplification, like was being done in the talk, you again find that you have this symmetry, like the x, y, the time direction is similar to the x direction, x plus y direction, and the x minus y directions. And then sort of you see you have this four-way symmetry, and I'm not sure like it is useful, but it definitely helps us understand it and sort of understand the fault tolerance protocols and how the information is flowing through these fault tolerance circuits.